Hello everyone, welcome again, another lecture. We're already, I guess, probably about a third nearly through the term since it's October now. If you can hear me, give me a thumbs up so I know that I've got a working stream here. Okay, good. Looks good. Thank you. So what we're going to do today is essentially chapter 6. We started already on that last time, but we're going to continue through just general solving of problems with Newton's laws, and then we're going to talk about friction and start solving some problems with friction. So just as a reminder, what we did last time, we were working on this problem, right? We were working on this essentially like the Atwood machine you just looked at, but with one block that is sliding, block 1 that is sliding on a frictionless plane, and then block 2 that's just falling, I guess, under the influence of gravity. So what we did last time is we wrote down the free body diagrams for block 1. So if I go back here, block 1 has is subjected to the force of gravity, so that's going to point down. There's a normal force that the surface here exerts on the block that's pointing up, and then there's a tension that pulls it towards the right. So that's this free body diagram. So the weight pulling down, the normal force pushing up, and the tension pulling to the right. And then for block 2, we have the mass. So there's going to be a weight that is pulling down, and there's a tension that's pulling up. There's no normal force now because there's no contact with any surface. So there's just going to be these two forces. So the tension pulling up and the weight pulling down. And we know that the acceleration on the first block to the right is A1, on the second block A2 downwards, but they'll have, of course, the same magnitude because they're connected with a string that has a constant length. So if the string has a constant length, then of course the velocities will be the same for M1 and M2 in magnitude, and then their accelerations will be the same as well in magnitude. So this acceleration to the right, or in other words, the net force divided by the mass will be equal to the acceleration, and then here the difference between the tension and the weight divided by the mass will be equal to the acceleration there. So let's write that down, those two equations. So we'll have for this let's call this sliding block and pulley. So we have one free body diagram. So for the first free body diagram for mass 1, we can write down that the tension divided by M1 will be equal to the acceleration, or M1 times the acceleration is equal to the tension. So that's from free body diagram 1 in the x direction. And for the other free body diagram, we have that acceleration which we have in the direction downwards. So that's going to be the weight minus the tension that we have to include. So M2 times the acceleration is the weight minus the tension. So that's from free body diagram 2. So it's important to make sure you have the signs right there, of course. So if that is equal to the tension, then we can just introduce the tension into the second equation, and we'll find that M2A is M2G minus M1A, and we can solve this for A as A is M2G, that's this term here, divided by M1 plus M2. So that's what we determined last time, right? What is useful now is to evaluate the limits. We already did that last time too, at the end of class, the very last minute. So what happens if M1 is much greater than M2, and what happens if M1 is much less than M2? And in that case, we found that in this case, if M1 is much greater than M2, then A will be about 0. If M1 is much less than M2, A will be approximately equal to g. So you can evaluate those limits. If m1 is much less than m2, then this first term here will be almost 0 compared to the second term. So then you essentially get m2 over m2. So that's 1. In the first case here, for m1 much greater, then this is essentially 0 compared to the m1 that we're dividing over. So we're dividing a very small number by a very large number, so we're going to find 0. And so this makes sense because in this case we have a very large block with, in this situation here, with a tiny block that is trying to pull it down. So that's of course not going to move. And then in this case we have a tiny mass that is sliding, and then we have our pulley here, and then we have a very large mass that is pulling down. So this will just accelerate as if that tiny block wasn't even there. So it's just going to accelerate as if it's in free fall with acceleration g. What makes sense is also to put this now in a little graph. So we can draw a little graph that gives us the acceleration for as a function of, essentially, let's call this m1 relative to m2, and so this is going to be small m1, this is going to be large m1, and so we start off for small m1 at an acceleration that's equal to g, and then for large m1 this gets closer and closer to 0, so we'll get a behavior that looks kind of like this. And of course we could just plot this versus m1 divided by m2, and rewrite this term in terms of m1 over m2, and then you could do this in a computer program that can give you that plot as well, of course. So it's going to be useful to evaluate these limits, because that allows us to verify that the solution we got indeed agrees with our expectations of what is actually going to happen. So that is going to be a very useful trick, and that's one of the reasons why calculating these calculating the symbolic expressions is going to be very useful. Instead of immediately plugging in the numbers, you could have plugged in m1 times a here. I mean, except in this problem you're not given any m1 and a, but you could have plugged in, if you had given, if numbers had been given for this this problem, you would have been able to plug it in there. You would have been able to plug it in here and here. Well, actually, I guess maybe not a, but so waiting with plugging in the numbers is often a benefit. The other benefit is, of course, that if I give you the same problem with different values for m1 and m2, if you had plugged in the numbers early and calculated, for example, m2 times g explicitly, you wouldn't be able to just replace at the end of your calculation the values for m1 and m2. You would have to redo the full derivation. So doing problems symbolically first and only plugging in the numbers at the end is going to save you time and give you additional insight. So try to do that whenever you can, rather than immediately plugging in the numbers. So let's look at a next problem now. So I already highlighted that one last time too. I showed you this graph and asked you to think about that. So we're not going to calculate the acceleration, but you would be able to do the same thing here, right? So now we are going to have a normal force in normal to the surfaces, but we're going to have it on both sides. We're going to have the weight that's vertically downward, weight always vertically downward, on both of the blocks. And then, of course, we're going to have the tension at an angle. So let's do that in a little bit of detail here. So let's, I don't know, carts on a slope, let's call it that. So let's say we have one slope like this and a slope like this. And I'm going to just introduce some angles here to make this a little bit easier. I'm not going to use the angles. I'm only going to use the fact that this is going to be a right angle. If that's a right angle, it makes the problem a little bit easier. So I'm going to put this mass m1 here, and then we're going to have our pulley and then our mass m2 is over here. So m1 is going to accelerate in this direction with a1, and m2 will accelerate in that direction with a2. And I've picked this this right angle here at the corner because now I can introduce just the coordinate system x and y, so that the surface on one side of the hill here, on the one for m1, is going to be along the x direction, and then the other side of the hill it will be along the y direction, and that just simplifies the formulas a little bit. Of course, you would be able to do it generally as well with any angle here, but for the purposes of demonstrating this, I'm going to simplify this a little bit. So on mass m1, what are the forces that apply there? So we draw our free body diagram. We've got the weight W1. We've got the normal force. This is the normal force. And we've got the tension, right? And the benefit is that the normal force is now entirely in the y direction. The tension is entirely in the x direction. And the weight, of course, is in a combination of the x and the y direction. It's going to be at an angle of 30 degrees away from the y direction. So that's one free body diagram. So now the other free body diagram for m2. So there will be a weight W2. The normal force will now be in this direction. I guess I should call this N1 and N2 because they're going to be different normal forces. So this will be, the normal force will be along the x direction, just like the tension here is along the x direction, and the normal force is along the y direction. And the tension here will be along the y direction, right? So just the choice of our coordinate system and the fact that I picked this right angle makes this a little bit easier. Since this is 60 degrees, this will actually also be, again, 30 degrees. So we have a very similar free body diagram in both cases. Of course, in the first case here, we're going to have an acceleration a1 that is in the x direction, and in the second case here, in the second free body diagram, a2 will be along the minus y direction. But the magnitudes will, of course, still be the same. a1 in magnitude is equal to a2 in magnitude, and will be equal to just the number a. So now if we were to ask what is the value for a, we can, of course, write an equation for free body diagram 1 for a. So it will be t minus, so mass times acceleration, m1 times acceleration will be t minus the weight, so m1 times g times the sine of 30 degrees. And then in the second case here, we have that m2 times a is the weight m2g times the cosine of 30 degrees minus t. And now we could extract t from this, plug it into here, and extract the value for a. And what you'll see is, of course, since we have a cosine and a sine, the expression will look a little bit more difficult, but everything else will be similar. And then, of course, we would go through the same situation of evaluating the limits. What happens if m1 is much greater than m2? What happens if m2 is much greater than m1? What I could do is I could have started with this as an angle theta, and then I could do things like, what happens if theta is 0? What happens if theta is 90 degrees? So in the case, if this is equal to theta here, the angle that the first plane makes, if theta is equal to 0, we end up in exactly the same situation we were in for the previous problem. In the case of theta equals 90 degrees, we actually have the situation where the blocks have now their roles reversed, right? So this is theta equals 90 degrees, and theta equals 0 degrees is essentially the mirror image. So if we go to theta equals 0 and theta equal 1, we should be able to recover that behavior of the previous problem. So again, it's a way to verify that after you've solved this problem symbolically, that you actually get an answer that makes sense, right? So generally a good idea to do that, to solve the problem symbolically, verify that when you take certain things to very large values and very small values, that you actually get the right answer, that it gives you the right behavior. Because it's easier to think in terms of, well, what happens if the mass of M1 is much larger than the mass of M2, or the other way around. And you can indeed use this in your assignments, and I encourage you to use this in your assignments. If you indicate, if you write your solution and you write down, I verified the limits and this makes sense, I'm not going to say you get bonus points, because the way the assignments are graded, there's not really any room for bonus points. But if this was an open answer question, that would give you the kind of leeway to maybe mess up on significant figures elsewhere and not get a point lost for that. Okay. So, next problem. So, the Atwood machine, we already talked about. I mean, you already solved this problem. This is, this is a fun little problem that comes back frequently. And of course, that's why it's a homework assignment, so you can work on it and really try to understand it. Another problem that we kind of did already with the tightrope walker is dealing with tension and masses that hang from a wire. So in this case, we're looking at a traffic light that's hanging from two pieces of cable, and they're hanging at different angles. So one is at 30 degrees, the other one is at 45 degrees. So the free body diagram here will have that 30 degrees and 45 degrees. 30 degrees here, 45 degrees in this side. So again, what we would do if we were to draw this free body diagram, so let's call this the traffic light. So we have one angle at 30 degrees with the horizontal, and then this one is at 45 degrees with the horizontal, and then the traffic light is hanging here, so that's just a mass. So our free body diagram is one angle, one force, or one tension in this direction, one tension in this direction, and then the mass, so that will give us the weight downwards. This will be tension 1, tension 2, or tension left, tension right, whatever you want to call it. This will be 30 degrees, and this will be 45 degrees. And one thing that the textbook indicated already is that we can replace these forces with T2x and T2y, and then we get rid of that one. We can replace T1 with T1y and T1x and get rid of this one, and that allows us to solve this problem more easily. So now we'll see that T1x must be equal to T2x, and T1y plus T2y minus the weight must be equal to the acceleration. Let's assume that the acceleration is equal to 0. A is equal to 0. So that gives us our two equations now. And of course, T1x and T1y are going to be related through the tangent of the angle of 30 degrees. So T1y over T1x will be the tangent of 30 degrees and similarly for T2, but then with 45 degrees. Again, that would be a way to then solve for T1x, T1y, or T1 and T2, including their magnitude and their direction. Well, we have their direction. It's 30 degrees and 45 degrees. Okay. So I'm going through these quickly because the mathematics of these problems is really not all that complicated. It's solving a system of equations. And actually, I encourage you to do that also when you're studying. Sometimes you can spend a lot of time doing the mathematics, which you know you can do, and the only reason why you would make a mistake there is not because you don't have an understanding of physics, but it's because you make a mistake in the mathematics. So I would encourage you to kind of separate those two ways of studying. So take some time when you're trying to really study the physics understanding of these problems, work through how to set up the problem, work through how to set up the free body diagram, how to set up the equations, but stop there and don't do the equations. You can, at a different part of your studying, you can focus on actually solving the equations and making sure you know that as well. But it's important, and it's probably more important for this course, to know how to set up the problem, how to come up with the free body diagrams, how to have your equations make sense. And so it's important to work on getting that skill down. Okay. Let's go to the next problem here. We can look at a problem like this, which is kind of a little bit an inverse problem. So we have a force from one tugboat and a force from another tugboat. They're both pushing in this case on a barge. And we know that the barge starts moving at an acceleration that is at an angle of 53.5 degrees with respect to the x-axis in this case. So let's assume that the barge starts from rest. So this acceleration is also going to be the direction of the initial velocity vector. And we know that the drag that causes the drag that the water exerts on this boat will be pointing opposite to the direction of motion. So it will be pointing exactly in the opposite direction as the acceleration. So this is going to be the drag. The drag is also going to be at 53.1 degrees, except it's going to be pointing in the opposite direction. So we can now calculate the drag, because we know that the net force, if we know the mass of the barge, we can calculate from the net force, from the acceleration, we can calculate the net force, and then the part of the amount that we would have to add to the net force to get to F1 and F2, that will be the amount of force that is coming from the drag, right? So so in our free body diagram, this is our free body diagram, we have our F2 and F1, the forces with which the tugboats are pushing, both along the X and the Y direction. And then FD will be in the direction of 53.1 degrees. So that will be 53.1 degrees off of the horizontal, but pointing in the opposite direction. So now F1 minus FD times the cosine of this angle is going to be the X component of the acceleration. F2 minus FD times the sine of that angle will be the Y component of the net force and give us the Y component of the acceleration. And so we will be able to solve then for the magnitude of the drag force. And since this all is in one line, we can actually write this down even more easily if we look at this. So we will have the total force F1 plus F2, F1 plus F2, let's call this force F. That force F is going to be this total force, F applied, I guess it's called F applied in the drawing. So that's the applied force. The drag will be the applied force, or the acceleration will be the applied force minus the drag. So mass times acceleration will be the applied force minus the drag. And since all of this is along the same direction, this is going to be valid also in magnitudes. MA is the applied force minus FD, and then FD will be the applied force minus mass times acceleration, and that immediately gives us our drag force. So that's going to be, so someone's asking what's FD. So FD is the drag force, is the force that the water exerts against the barge to prevent it from moving, to trying to oppose the motion of the barge. And this is always going to be in the opposite direction as the direction of motion, as the velocity vector. And so in this case, when the barge starts moving from rest, the velocity vector will start to point in the direction of the acceleration. Okay. So yeah, this is maybe the first example of kind of a force similar to friction. Drag and friction are similar forces. So I think I'm going to skip this problem here with the luggage carts, which is really just normal forces and weights and tensions between the different components. So that's going to be very similar. And let's jump to friction, which is going to be the next big part to talk about here. So friction, similar to this drag force we just talked about, is any force. So let me just write that down here, and I'm gonna keep this up because someone was asking for that. So friction is any force, is a force that opposes the relative motion between two objects. Between two systems that are in contact with each other. So you can think of that as, for example, the barge and the water. Those are two systems that are in contact with each other. But of course, another example is just one thing sliding over something else. So a crate sliding on the floor. If you're trying to push, or if you are pushing this crate in this direction and it's moving in that direction, there is motion or attempted motion in that direction, then the friction will be pointing in exactly the opposite direction. And of course, the reason why there's friction is microscopic in nature. There's little imperfections in the surface, and they start to grip into each other, and that is what is going to cause this crate to have difficulty moving, because it needs to kind of get over these little bumps in the microscopic surface. So microscopic motion, essentially, or microscopic imperfections, those cause a friction, a macroscopic force, and this I'm going to write described by a macroscopic parameter, and we're going to introduce that parameter in a second here. So someone's asking, what about the motion of cars? If you were to push your car forward and it's not rolling its wheels, the handbrake is on or something, the parking brake is on, then you would have friction between the wheels that don't want to turn, and the street. So obviously friction is going to be a very powerful force to prevent you from moving the car. Of course, if you are moving the tires, if the tires are turning because the engine is running, and because you're driving, then the friction will prevent the car from slipping. So let's say you're on ice and you start the car and you're a little bit too heavy on the gas. It will start slipping, right? So then friction is not, there's not sufficient friction to prevent that motion of the tires, and so they're just starting to slip. There's two kinds of regimes in which friction is it behaves. So there is the so-called static friction. So static friction is when objects are not in motion yet, or not in motion, period. With respect to each other. So one example is when you're pushing this crate, and it's a heavy crate, and we'll see why heavy crates behave this way. A heavy crate, you keep pushing and pushing, and it doesn't want to move because there's too much friction and you can't make it move. So static friction is when that is happening. Kinetic friction is when the two objects are moving with respect to each other. So this is when the crate, maybe you get a friend or so, and you respect to each other. Maybe you get a friend to help you push that crate, so you get the crate moving, and at that point there's still going to be friction that prevents you from, or that slows you down in a sense, that provides a force opposite to the direction in which you've gotten the crate moving, but it's going to be a force of kinetic friction. And static friction is always going to be greater than kinetic friction. In other words, it takes a larger force to overcome the static friction, but once it's moving, you can maintain the motion with a smaller force to overcome the kinetic friction. This is a property of friction that is very general, and in particular when talking about contacts between surfaces. And so, this is a way that we can describe that. So we have our block here. We apply an external force. There's going to be a force of static friction that, as long as the block doesn't move, as long as there's no acceleration, we know exactly how large the static friction has to be. It has to be exactly the opposite as the force that is externally applied, so that the acceleration will be equal to 0. Once we have motion, the force of kinetic friction will be potentially smaller than the externally applied force, and this force of kinetic friction will be slowing down our object, because otherwise, because of friction. So the force of friction, in a sense, so as long as if we look at the force of friction versus the externally applied force, if we apply a 0 force, then of course friction is going to be 0. If we increase the force that we apply until this point here, until the maximum of static friction, there will be no motion. At that point, if we apply a little bit more force, or at that point we get into the kinetic region, the block starts moving, and then we only need a smaller force to keep that motion. So this is going to be the kinetic friction. So this also indicates already the mathematics or the mathematical expressions for this friction. So if we write down, let's see, static friction there. So static friction will be a force Fs, and Fs will be as large as necessary, as large as necessary to prevent motion, but as long as Fs is less than or equal to mu s times the normal force. So this is the expression for static friction. It is as large as necessary to prevent motion, so to maintain a equal to 0, zero acceleration, but it is going to be at most as large as mu s times n, where mu s is the coefficient of static friction, and n is of course the normal force. So friction is proportional to the normal force, and that of course explains why a crate that's heavier, which will be subjected to a larger normal force, why a crate that's heavier is more difficult to push, because the mu s times that normal force will be larger. And if we think about that in terms of what happens with the normal forces, if there is a larger normal force, then those imperfect surfaces, those rough surfaces, will actually be closer together, and there will be less, there will be more places where they're actually going to contact each other, and those are the little bumps and imperfections that are going to increase the amount of friction. So that's static friction. It's as large as necessary. And then kinetic friction. So kinetic friction is always Fk is mu k times the normal force. So the kinetic friction is always the same magnitude, now no matter what situation. It's going to be mu k times the normal force, and this is then the coefficient of kinetic friction. And just to give you an idea, there's a couple of different values for the oops, I went back to the slide. There's a couple of different values for these coefficients of kinetic friction. So for example, rubber, a tire, for example, on asphalt, on the road, that will be mu static is about 1. So the force of friction, of static friction in a car is approximately equal to the magnitude of the normal force of a car. So given the weight of the car, you can of course calculate what that force of friction will be. So that's a large amount of friction. If we then look at another extreme, steel on ice, or an ice skate on ice, when in motion, the kinetic coefficient of kinetic friction is 0.02 approximately. So only 2% of the magnitude of your weight is the magnitude of the force of friction is only 2% of the magnitude of your weight. So that's a small force of friction, and that's of course why the coefficient of why ice skating is typically considered to be nearly frictionless, because there's only 2% friction. Is it possible for Fk to be equal to Fs? Well, there are going to be cases where mu s is very close to mu k, and so in that case, Fs and Fk will be very close as well, and within the significant figures that you consider, it might look like Fs and Fk are the same, but fundamentally you cannot have static friction be smaller than kinetic friction, because that would almost make it preferable for objects to move with respect to each other than to be static with respect to each other, and that of course doesn't make sense. So there are tables for these friction coefficients that you can either Google, or there's a table in the textbook for some of the problems, which includes the coefficients of static friction and of kinetic friction that you'll need to use potentially in problems. So when an object moves with constant velocity, then it's kinetic friction that applies, right? Let's say, and we're going to do these kind of problems on Wednesday. So, let's say here, we're going to look at this example of a snowboard glider. So there's going to be kinetic friction that applies, that's mu k times n, that is going against the direction of motion. So it's pointing upwards, or along the slope, upwards along the slope. And so in this case, the question is to calculate acceleration, but this person might as well have zero acceleration. And if this person has zero acceleration but constant velocity, then we would still use the coefficient of kinetic friction, because the person is moving with respect to the snow underneath the snowboard. Okay, that's it for today. So we'll start off with the snowboarder on Wednesday, and we'll talk to you on Wednesday.